Hello my friends, welcome to this sixth video of the series Consciousness as a Modular Phenomenon. In this video we will make a kind of the tour of the path that we were following. It's talking about the consciousness and about the observables properties of the consciousness, because we need to build a little bit the mathematical machinery that will allow us to make further progress in the topic. As we saw last video, the language that the mathematical language that we are going to use to talk about the partitions that are associated to consciousness as we define it, and the language that we are going to use is the language of Riemann surfaces and complex analysis. So it will be more clear why we are going to use this language, this specific language, to talk about partitions, and not, for example, to focus only on the topology, the topological diagrams that we were defining in last video. In last video we defined the topological diagram of this mapping between two spaces, one that contains all the partitions associated with partitioning of the object that I am being conscious of, and the projection and the superposition of all those partitions, the sum of those partitions on a base space, which is the space where my conscious sensations or conscious processes live. The real process that we feel, that we are conscious of, they live in this base space, which is the projection of all those superposition of partitions. Okay, now we were led to this diagram through a topological representation of fiber bundles, because fiber bundles, as we said, are ideal topological objects that encapsulate the idea of a tower of an equivalent class of, for example, partitions. What the important thing that we discuss is that there is a group in all this machinery, in that diagram, that is hidden there, and the group is the fundamental group of both spaces. So the mapping between both spaces is a group homomorphism. That means that respect the composition of loops in both spaces, because the fundamental group is a topological group, let's say, that lives in both spaces, and it's the group of loops, of operations on the loops in both spaces. So the interesting thing is that this diagram will be with us until the end of these videos, because it's the base for all the rest that I want to, let's say, to introduce. The idea is that these partitions that we generated, the partitions and equivalence classes are the same thing. So, like I said, equivalence classes immediately lead us to talk about fiber bundles, and fiber bundles immediately take us to speak about this kind of diagram with this projection. And so the topological structure that you have there, this topological structure given by the fundamental group, and this group homomorphism that maps the larger space, let's say, into the base space, the space of cosets, let's say, and this language, let's say, this diagram, let's say, that we use for representation of these topological relationships encapsulate all the information that we can have from the topological point of view. But now what I want to do is to use a language that will enrich this situation to give us enormous amount of information, because what we are going to use is, instead of using simple spaces, one mapping to the other with equivalence classes and this group homomorphisms, what we are going to use is the mapping between the so-called Riemann surfaces to a Riemann surface. So imagine that we, instead of imagine this diagram that we have with the larger space and the base space and this group homomorphism mapping from one to the other. This homomorphism, I call it pile. Remember this terminology that we use. So imagine that now we complexify both spaces. Instead of kind of imagine that we have real points or real coordinates, for example, for those in those spaces, we can imagine that in the neighborhood of each one of the points of those spaces, there is a kind of coordinate, complex coordinate structure, a kind of chart is called, and in the neighborhood of each one of the points in both spaces, we kind of complexify. Instead of considering kind of real coordinates of normal coordinates, we consider complex coordinates. So we are jumping then into the arena of complex analysis, because let's say when we do that, this complexification, let's say, what we are is a generalization. It's a generalization of the topological description that I said before. In general, Riemann surfaces is a generalization to complex analysis of a normal topological situation where you have real coordinates, for example, real charts covering a manifold or a surface. Instead of using real coordinates, you use in the chart, you use complex numbers. So the most interesting thing is the following. I mean, you have, for example, imagine that you have functions from from the complex number into the Riemann surface. The Riemann surface will be the base space in our case. So what we are going to do is this mapping that connects both spaces. It becomes a function. It still is a group homomorphism of the fundamental group of both spaces, because topology is more general, let's say, it's more abstract, let's say, than this complexification that we are doing. We are just adding structure to those two spaces that we map one to the other. And the interesting thing is that what we are going to say is that the addition, let's say, that we have to do to talk about Riemann surfaces, so this base space becomes a Riemann surface, is that the analytic functions in the larger space are mapped into analytic functions in the base space. So this, I will explain a little bit. Analytic functions, for the people that knows complex analysis, I mean, is something known. Analytic function is kind of the functions that are differentiable in the complex plane. That means that they are the derivative, let's say, the derivative exists independently of the direction I come in the complex plane. So the property of the differentiability in the complex analysis is much more stronger than the differentiability in the real case, because it constrains enormously the kind of functions that you can have. Not many functions are going to be analytic, and in many cases, when you have certain, let's say, constraints, the only function that can be analytic is the constant one, for example, and so it constrains a lot the kind of functions that you can have with this property, let's say. But in the real line, let's say, you still have the normal differentiability, like always. So the interesting thing with Riemann surfaces is that imagine this diagram that we were discussing before. Now both planes are kind of complex manifolds, and this mapping between them both not only is a group homomorphism of the fundamental group of both spaces, but in addition, it maps homeomorphic or analytic functions from one space to the other. So, and this, like I said, this constraint is so strong that the functions, if you consider any analytic function living in the larger space, let's say, the two constraints together, that it is a group homomorphism of the fundamental group, this projection, according to equivalence classes, no? And the fact that the mapping maps analytic functions from the larger space into the base space, also analytic functions in the base space, this constraint is so strong that the functions that you can really define in the base space, they are very constrained. I mean, in fact, there will be one function that can generate the full, let's say, the full set of functions that can live in the base space. If you map, I mean, it's so constrained, the mapping, that there is only one generating function in the base space that can satisfy these conditions. I mean, when you map these functions, I mean, the interesting thing, I mean, important thing, why we are interested in the functions in both spaces, in the larger space and in the base space, the projection space, because remember, for example, the Klein approach to the study of geometry or topology. That says that if you want to study topology or the geometry of a space or a manifold, for example, you have to study the functions that can live in this space. So that's why we are interested in exploring, for example, in getting much more information about these two planes, and especially about this base space, because this base space, like I said, is the place where my conscious experience lives. Like I said, this projection is a superposition of partitions. That is, the partitions live in the larger space. According to some equivalence class, they are vertically projected, like in a fiber bundle projection. And the point where they land, this point is one point in my consciousness, let's say. Of course, not mine, but consciousness in general. Now, because this is the mathematical representation that I wanted to give to a structure that I want to give to the conscious states. They are a kind of superpositions or partitions of the system that I am observing, for example. No? So, now, why we are interested in this Riemann surface, the one we are projecting in? I mean, the larger space can be a general space, can be the full complex, for example, plane, and you have all the functions living there, the homomorphic, meromorphic functions living there, all the analytic functions living there. And what you do when you project is that only some analytic functions, not many of them, in fact one, can live in the Riemann surface. Why this is important for us? Why this is interesting for us? Well, because if I say that this base space where I am projecting is where my consciousness lives, then I will have to have some kind of characterization point to point in this space that will allow me to assign to consciousness, to my consciousness or the consciousness of the that is projected in this point, that will allow me to assign some kind of function to it. Some kind of, if I want to say something about this conscious point here, I have to have some quantity defined there. And this quantity has to be a function of the coordinates, of the complex coordinates in this case, of this Riemann surface. And the interesting thing is that if I want to say something about functions here, and I require that it is analytic, because it's the most useful kind of functions that I can have, then these functions are completely determined. In fact, there is only one function. We will see, because it's exactly, we have to discuss a little bit about Riemann surfaces, about invariants in functions on those Riemann surfaces, so to motivate the idea what is it. But I want to just to motivate why it is important for us for the topic of consciousness as we are trying to study. Well, the fact is that if this point where the projection of the lands, this point, if I want to say something about that, I have to have some function there. And this function is completely well determined. It's an invariant of certain transformations that we are going to see in this Riemann surface. In fact, it's the so-called Möbius transformations that live invariant the Riemann surface. One specific Riemann surface we are going to talk about. And this function is called a J function. Is the generating function for all the possible functions that can live in this Riemann surface. So you cannot, you don't have the freedom that you have in the larger space, that you can have any analytic function there. Only certain functions, and in fact one, can live here in this. Not one, but one that is generated by one function, the J function, the so-called Jacobi function. Jacobi function. So we are going to discuss about these things, but I want just to motivate the idea why it is important for us to have much more structure in this base space when I project it. And that's why I am interested in introducing the language of J functions, about Riemann surfaces, because this structure additional that we gain when we speak about this base space as a Riemann surface, it gives us enormous amount of information about how to talk about this projection. Because what we are doing is talking about the projection. This is what we are interested in. How we form the conscious experience from all these partitions that we form. So if this projection is contains, if I have more information, let's say in all this diagrammatic topological description, if I introduce more information through the complexification, through the properties of the Riemann surfaces, let's say, it's a kind of generalization of the diagram that I had before. So we can do it. It's just a generalization, like a Riemann surface is a generalization of other kind of surfaces, for example. But this generalization, like always when we do complex analysis, will give us enormous constraints on the theory. And it gives us something precious, that is these invariant functions on the Riemann surface, which before we didn't have that. I mean, when we were speaking about the topology, I mean, we wouldn't have that. Only when we start speaking about complex analysis, we complexify, let's say, the coordinates in both spaces, we get these kind of functions that are unique, and since they are invariant, and what we will see, they encode and they explain all the observables of consciousness. If we start assigning to this, like we did before, this is the space, this larger space is a space of partitions. Partitions that I form when I partition, let's say, the objects that I am observing. The landscape or object that I am being conscious of. So this is the space, and as we saw, for example, in our brain, how we form conscious experiences from those partitions is by superposition for all of them. An enormous tower of superposition, and through some equivalence relationship that we are going to define later, but that now is much more clear the origin of this equivalence relationship, because first of all, I mean, we have already a group there that allow us to make partitions of the, I mean, equivalence classes of this. We have these equivalence classes through the orbits of the group, of this group, in both surfaces. So this, let's say, the origin of the equivalence classes is exactly that we have a group there. And then if you have a group, you can always define cosets of the group. That means equivalence classes. And those equivalence classes are the ones that are projected vertically, let's say vertically. I mean, they are projected by this mapping that is a group homomorphism. Now, I mean, this is the plan. The plan is to use the J function, the invariance that is unique, and this is, you will see all the properties of consciousness will be associated to properties of the J functions. The robustness and uniqueness of the self-conscious experience, they come from the uniqueness of this J invariant. It's unique. You don't have any other generating function there. It is completely constrained. And many other properties, like you say, like you will see the holographic, let's say, properties, they are very clearly defined through the properties of this function in this Riemann surfaces. So you will see all these properties of consciousness, of these observables of consciousness, they can be somehow related or mapped to properties of this J function. In fact, the J function, it will be a kind of characterization of a conscious state or conscious process. Multiplicity will be related to the fact that the Riemann surface itself is different according to the charts that I am assigning, and so changing a couple of parameters there, you get a different Riemann surface. That means a different J function with that are, let's say, not equivalent to each other, which generates its own evolution, let's say, its own world, let's say. So that's all these properties of the J function, we are going to be able to map them to properties of those observables of consciousness. So that's more or less the plan. Just by now, I want just to introduce informally this the ideas of the Riemann surfaces and why it is important to us. Now, the complex torus is itself homeomorphic to the upper half plane, to the complex upper half plane. So if you take the complex plane, the plane of complex numbers, and you take only those with imaginary part larger than 0, so all the upper half plane, you can prove that the the complex torus is homeomorphic to the upper half plane. When you start studying which functions can live in the if you have the mapping of those functions, analytical functions, through all this preserving the analyticity and having this mapping of classes of equivalence, these vertical projections, what you find is something interesting. If, for example, you consider functions that has no infinities, I mean no poles, they're called in the complex analysis, no infinities, no divergences. If you consider only functions like that in the original space, so there is only possibility in of function that can live in the base space, in the complex torus. And this is the constant one, the constant function. No other possibility. So to get something more interesting, you will have to consider functions that has poles, that has infinities, complex infinities. So the interesting thing is that what you can prove is that the functions having poles, they will have always poles of order 2. So if you make a Taylor, a Lorentz series of this, they will have up to power -2, let's say, in the Lorentz series of this function, which is analytic, so you always will be able to make a Lorentz series. Then, interesting thing, they will have poles of order 2, and these poles will be located, they will be periodic in a lattice into this upper half place. So let's say that the poles will be in the borders of a parallelogram lattice that is repeated with a certain period, let's say. The period is one, just let's say, just you always need to know that if you have, for example, a small parallelogram in the upper half plane, and you repeat this parallelogram, you translate it, you use the symmetry of translation, let's say, you are going to be able to cover the full upper half plane, and then in the as we have a kind of relation isomorphism between the torus, the complex torus and the upper half plane, then you can cover the full torus also. Then, which is more or less evident, because what you do is to take a strip in the torus that is covering a part, and then you move it over the torus and kind of you cover the full torus. So that's more or less what is happening with this parallel. It's called the fundamental parallelogram. And the interesting thing is the following. So the functions in this, you take only one parallelogram because it's the only thing that interests to you is the functions will be periodic. This is the other thing. And they will be double periodic, they are called, because they are periodic in the direction, in the vertical direction of the parallelogram, and also in the horizontal direction of the parallelogram. So they are double periodic. That's why they are called double periodic, because they have two periods, let's say two complex numbers, kind of vectors, let's say, that defines this parallelogram. And the interesting, I mean, this is just because of the topology of it comes from the topology of the complex torus that you can define this parallelogram. So the interesting thing is that the functions that live in this space, they must be double periodic and have poles of order 2. And the poles must be located in the border of this parallelogram, as you move this parallelogram to cover the full upper half plane, you get a lattice, and then inside the fundamental parallelogram, the functions, the function. So you need to study only what happens in the fundamental parallelogram, because what happens in the rest of the upper half plane will be exactly the same, only that you move this function somewhere else. And then the other interesting thing is that inside this fundamental parallelogram, the function is well defined. It has no poles, and this is an interesting thing. Let's say, so you can study this function, and what you get is that this function is, I mean, when you study which is this function, you try to find this function, you will get a kind of differential equation. Because of this periodicity that you have there, you will get a differential equation for this function inside this domain that is called the definition domain of the function. The domain is the function is the part of the plane where the function is well defined. It has no poles, so it's inside this fundamental parallelogram. This is the domain of this function, and you only need to find there, because in the rest will be exactly the same by translation. And then the interesting thing is that there will be because of this periodicity, you can find a differential equation for these functions, and the differential equation has a kind of it looks like the equation of elliptic curve. The elliptic curve are kind of cubic equations in two variables. Let's say it's called elliptic curve because the equations of the elliptic curves are of the same kind of cubic form that you get for this differential equation of these functions, and that's why these functions are called elliptic functions. So it's a very strange, I mean, very far, let's say, but it has something to do with the elliptic curves at the end of the day, because you will analyzing what happens with this cubic function, differential equation, you will have to study a little bit of the elliptic curves to try to define the properties of this function, I mean, to solve this equation. So when you solve this equation, you are left with something that is called the phi function, the Weierstrass function. And this function is well defined in this in the fundamental parallelogram. And then you find it, and it is unique. It is unique. You only have one possibility for that. So now the interesting thing. So in addition to, there are transformations that leave the upper half plane invariant. Those are the so-called Möbius transformation. functions of two variables, exactly like this Weierstrass function. And the interesting thing is that they leave the upper half plane invariant. And so, as we remember in this claim, let's say, approach to geometry and to when you study the invariants, I mean the functions that are invariant under certain transformation that leave the full space. These are the so-called automorphisms of the space. These automorphisms are very important because of the group theoretical, let's say, properties that we have from this fundamental group. And then the interesting thing is the following. If you find, for example, the orbits of these functions that leave invariant the full you can kind of partition the full space, the full you can partition the full Riemann surface into domains where the function will have exactly the same value. You start with the fundamental parallelogram, and you apply the Möbius transformation, and this will land in some other places, some arc, some kind of semicircle, let's say, somewhere over this parallelogram. There will be a new domain which has the same values. The function has the same values because it's invariant. I mean, this transformation leave invariant the function, and then they leave invariant the function up to some powers, let's say. And then the interesting thing is, I mean, these Möbius transformations that do this are kind of describing the orbits of this fundamental parallelogram. And when you start mapping the orbits of this fundamental parallelogram, what you are defining is a coset, let's say, the equivalence class of this fundamental parallelogram, let's say, on all over these transformations that are group automorphism of the over the Riemann surface. So they defined equivalence classes, cosets, let's say, of this group of transformations, because they form a group of transformations. And this group of transformations, they are isomorphic to a matrix group that is called SL2C, the special group of transformations of 2 by 2 with complex numbers. The four, let's say, numbers in the matrix are complex numbers, and the determinant is different than 0. And this group of transformations, they kind of define the orbit of this parallelogram. And at the end of the day, when you have the full orbit, let's say, it comes back to the parallelogram. So what you have is a band in the, I mean, you find that this parallelogram gets mapped by these transformations into a full band of the plane, of the upper half plane, and it kind of partition it in several smaller domains where the function has the same domain. So this unique function, this Weierstrass function, gives rise by this completion by domains. I mean, you define a new function that lives, has the same values in all these domains, and then you can find a different function using the Weierstrass function. You can find a different function that will generate all the possible functions that lives in this kind of space, this kind of partition space. I mean, in the Riemann surface. And long story short, I mean, you can find that there is only one function that generates all the possible functions that are invariant under this group automorphism of in the Riemann surface, these Möbius transformations, this group of SL2C. There is only one function that is invariant under all these transformations, and so when you can construct this function, and this function is called the Jacobi function, and it's a two variables function or a one variables function if you consider only, because it's two periodic, you can eliminate one period through a kind of transformation there, and you have one function that is in reality with one variable, and then this function is unique and it characterizes each point in the Riemann surface. And interesting thing, I mean, if this function is associated one-to-one to the Riemann surface. For each Riemann surface, you will have one J function. If you change, for example, the variables, you change the variables in the J function, or you change the variables in the J function, you don't map. I mean, if you do the inverse map, I mean, you try to find out which is the complex torus corresponding to this new J function is another torus. Each torus is associated to two values of the complex number, the two complex numbers. Because it's like, imagine a torus, you have two variables. I mean, you have one variable that is the big radius of the torus, and the smaller radius is another complex variable. And then if you change those radius, you change the torus. You are changing the torus. This mapping of these two radius is exactly what we represent in this parallelogram, and also in this J function. The J function is a two periodic function. I mean, these two periods, these two are complex numbers only that are associated one-to-one to the torus. So this is, you can understand it with this big radius and small radius of the torus. These two are these two complex numbers. If you change them, you change the torus. It's another surface. And that's exactly the analogy that I want to start making. If you change this, if you change the invariant, you change the variables in the J function, you use other values in the J function, you are going to get another torus, another Riemann surface, another base space. And that's the point that I want to make. This function, this J function that is a characteristic of the points of this Riemann surface, is associated one-to-one to one Riemann surface. If we change the variables in this J function, you are talking about another Riemann surface, another projection of the larger space. And that's the property of uniqueness of the consciousness. Why it is unique consciousness? Well, because in reality the projection space, the Riemann surface where I'm projecting, is unique. I mean, if I change the J function, which represent, let's say, if I want to say that consciousness is somehow tied to the J function, because it's the only function that I can define there. It's the only function that I don't have a freedom. And that's important. It's so constrained, it's so robust. And that's the other property. It's so robust. The J function is so robust that it's unique. I don't have a freedom. But if I change it, I am changing the Riemann surface, the complex torus I am talking about. And this is the property of uniqueness of the consciousness. So you see two observables already: robustness and the uniqueness of consciousness, of the self-conscious experience. So now it comes the big, let's say, the big association that I want to do, because all this diagrammatic representation, this topological representation, this was given by default by the way we constructed. I mean, but saying that partitions are involved in the conscious process, let's say. This is all automatic. And now comes the first, let's say, principle, let's say. The first big principle. And I want to, this is one of the first point where I'm going to introduce it. I want to say that consciousness is characterized by the shape function. The shape function encodes somehow information about consciousness itself. It is something that is invariant. In the evolution, suppose you have a point that is evolving in this Riemann surface. So kind of if I made the association, so my conscious state is evolving in the Riemann surface, but the shape function is the same. The shape function is the same. It's changing values, yes, but it is the same function. And then that's the point, what I want to say. I don't have a freedom to choose this shape function. It's unique, and it's the only good function in this projection. If I make the complexification, I mean, if I want to extract more information. And it's unique, it's robust, and what I want to say is that consciousness is characterized one-to-one with this shape function. I know it is a big thing to say, but if you think, we have done everything logically. I mean, there is no freedom at all. And if I want to say something about this point of projection, I have to have some quantity there. And this quantity has to be independent of everything but the conscious state. Independent but of the surface itself where I am projecting. It doesn't have to have kind of the structure, to feel the structure of the larger space, but it has to be kind of invariant. Exactly, it has to be an invariant of all the transformations that I can do in this Riemann surface. So, because my conscious experience goes with me, it is invariant. It's something that from point to point in this evolution, in this Riemann surface, should be something that is not changing. It's changing in value, but it's not changing in form. And the only such good function is the J function. There is no other possibility. If I want information about this point, base point of the projection, and I define it in this way because it's a projection of an equivalence class, if I make it like that, I have no choice. The J function must be telling us something about our conscious state, our consciousness. And I want to propose that it not only says something, it is characterizing with a function. Kind of, you can call it a field, for example, conscious field. I don't want to call it like that because it looks strange, but it will be something like that. It's a function that says about the summation of all these partitions in this Riemann surface. So that's one of the main points in all this theory. Of course, we are going to discuss much more about these things, because at this point I know it will be completely polemic, but if you think, we have not done anything out of the mathematical law. We have used mathematics, and if we want to say something about this mysterious thing called consciousness, and we want to think consciousness as kind of superposition of partitions of the observed world, there is not much other option. Partitions are equivalence classes. Equivalence classes take us to fiber bundles. Fiber bundles take us to this diagram. If we want to get more information from this diagram, we complexify it. We generalize it to Riemann surfaces. And in the Riemann surfaces, there is only one possible function living, invariant function living in the Riemann surface, the J function. It generates all the other functions, invariant functions. So if I want to say something about the points there, which are my conscious experience, I have to use the J function. And the J function is characterizing the conscious evolution over this Riemann surface of the plane where I project. So I will leave it like here, because it was a lot of information today, but this is one of the main points in all this theory. It's the starting point in reality. As you saw, we are going to exploit a lot this J function property, because the enormous properties that it has, the enormous connections with many other areas of mathematics and physics and everything, will allow us to make a lot of extraction of information about our consciousness. If we say that consciousness is tied to the J function, then we have an enormous tool in our hand. And I want to motivate, I want to prove somehow that this makes sense. I hope you already, from this video, you got the sense that it is somehow is natural, let's say, to do it like that. It's a kind of generalization of the normal projection of this topological diagram. And but you will see the power of this, because of course the power of the J function is unbelievable. The connections with all the other areas of mathematics, you will see the kind of unbelievable structure that we are getting from that. I mean, the richness of the structure that we are getting from working with Riemann surfaces. So let's leave it here. I think it's more than enough for this video, and in the next video we are going to continue talking about Riemann surfaces and exploiting the properties of this new way of speaking about these partitions and about consciousness. Thank you.